this talk was really hastily prepared. The last time I gave it, it was 40 minutes, but my co-author was in the audience, so maybe this time would it be quicker? I don't know. Questions will come at the end. So this is going to be the 422 Toric Code.
What do you mean by that?
What does it really mean? Is it relevant? Is it interesting? Hopefully we will answer these questions in the positive. Thanks to Nodar's good setup. So let's reveal some stuff. All right, so we're going to get introduced to surface codes and color codes in like 2 slides. So just let it in and try to wedge the information into your head. Then I'll set up a little toy scenario, which is going to appear ridiculous to experimentalists, but the last time I gave this talk, it was in front of theorists. So they thought, oh my God, there's actual images of superconducting circuits. This must be really well grounded. It's not, and you'll know. But yeah, they had a completely separate set of objections to the talk. Then we get into what the actual code is, get distracted with other codes, then get undistracted, and then we stop. Okay, so first, that's a giant picture of my head. Oh my, why should you listen to me? So I'm a postdoc over across the street at the AV. I'm in the Bertels group, and I get called a domain expert, or quantum guy, or an oracle, or whatever all the time. Because my job is kind of to take engineers' questions and produce meaningful answers. So if you have questions for someone who might know a little about quantum error correction, and you think you need a meaningful answer, feel free to find me. And if you have any questions about this stuff as well, so I'm interested in the intersection between quantum error correction and actual physics. Anywhere where the implementations of quantum computing limit or expand the set of techniques that you can use for quantum error correction. I'm interested in those spots. So if you have a really difficult to implement code or a measurement that gives you more than 1 bit's worth of information, I'm interested in all that stuff. And then I do a bunch of programming as well, and I'll take practical questions. Find me over the internet or in real life. So let's get to work. So quantum error correction in 1 sentence. You can take a big number of qubits that aren't that good and simulate 1 qubit that is much better. That's the entire goal of quantum error correction. But in order to do this, your bad qubits have to be not that bad, and you have to do some pretty good operations on them. So you're allowed finite noise on every component and every operation, but not too much. And then with those criteria met, you can expand and get something arbitrarily good at the cost of only using more qubits and maybe more time. That's the idea. There are some additional considerations that go into making a protocol that's popular at QuTech. So if your qubits move during the protocol, people don't like that because then they can't put them on a chip or embed them in a diamond or pattern gold and then leave some stuff there. They would have to kind of juggle, and no one likes to juggle. Also, if you have a protocol that involves doing a ton of operations on the same qubit over and over again, these things take time, and errors accrue in time. So if the amount of time you spend increases as you increase the size of the protocol, that's also no good. Oh, and these are the special theorist words that get used to describe these things. So if you encounter a theorist in the wild, you say the code is LDPC, and they get you and they'll respect you. And that's like a little secret. You don't have to tell anybody that I told you this. They're videotaping these talks? Is that right? Yeah, okay. So the jig is up. I'm sorry, everyone. The theorists will know that you're trying to impress. And then it helps also if the physical qubits can be embedded in some 2-dimensional surface, with constant distance between all the nearest neighbors in like a regular grid. Because those things are easier to construct than a 4-dimensional tetrahedron or hyperbolic piece of lettuce on which you embed the qubits. And so we stick to things that are like the most vanilla possible most of the time. And so there are 2 popular options for this. There's surface codes where you have local operators that are defined on these squares. Qubits go on the corners. And there's like an x square, so it's x, 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 and z, 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 z. And if you measure those local operators, you'll get information about whether you're in the code space or out of the code space, and how to get back in the code space so that you can correct errors as they occur. And then here's a very similar code called color code. Here there's an XX, XX, and a ZZ, ZZ on each of these tiles, and there's a weight 8 pair of these operators on this octagon as well. Qubits are on the vertices again. and they're slightly different. We'll compare and contrast in a minute. So, surface codes tend to have operator weights that are minimum 4, and then color codes tend to be a minimum of 6. You can get some that have squares in them, but then they also have to have octagons. But you could get an all hexagonal lattice. You can do gates on these codes some of the time. You get a Hadamard and a phase gate on a 2D color code, but you don't get the Hadamard or the phase gate on surface codes. There's an asterisk where it says there's no transversal gates, because C0 is transversal, but you would have to pull two two-dimensional codes, one on top of the other, in order to make a transversal gate, take a constant amount of distance between each qubit. Otherwise, you'd have to hop all the way from this qubit over to that qubit, leapfrogging the rest of the grid. Okay. And then, let's see, the other thing really that people care about is that the noise threshold for operations is around 1% so far in surface codes, but it's around 0.1% for color codes. And I'd like to let you all know why this is. This is probably because it's tough to decode color codes. The reason it's tough is that for surface codes, you get pairs of syndromes. So if a bunch of errors happen on a wavy line, like a bunch of qubits in a row are all messed up, you get a pair of endpoints. And that's really easy data to handle because the weight and therefore likelihood of an error is just proportional to the length. Yeah?
Can you give us some intuition for why they call color codes? Surface codes, it's one can...
So why they're called color codes is because 3 colorable graphs are used in their construction. The color doesn't change the type of the stabilizer or anything, but if the surface is 3 colorable, that guarantees that the stabilizers commute. So you can turn stabilizer commutation into a little graph theory problem. And we leave the colors on there for the rest of the paper. It makes your figures look better. But nothing about the red tiles and the green tiles is especially different in terms of what circuits you would do or what stabilizers you're trying to measure.
Okay.
Right. So you have kind of a linear problem where you're trying to unite 2 of these syndromes with a weight, say 5 chain, and then kind of minimize the total weight that you unite all of the pairs of syndromes with. This is a well-studied combinatorial problem that was solved 50 years ago, so we don't need to get into it. But when you have a color code, you can have a little, if you see this little light gray pattern of errors here, there's 3 of them, and it anti-commutes with 3 of these stabilizers. So you get a triple of syndromes, and you would have to try and find the optimal, or like the smallest letter Y that goes into making that syndrome. You're going to find a minimum weight, and therefore likeliest error. That's an NP-complete problem, so you have to do some workaround in order to try and solve it. And there you lose some efficiency in the decoder. Also since these are tougher algorithms to write, surface code decoders are way more mature. More people study them, so there's a sociological effect as well. So, now that you guys are all experts in 2D topological codes, let's move on to the scenario that I want to consider. I'm hoping not to get any objections from real experimentalists. But if you work with superconducting qubits, you should read this paper. That I can say with confidence, because it's pretty expansive, and it goes over a lot of the basic physics that's still used today. Wow. Yeah, at least for transmons. But the thing I want to highlight is that there are multiple implementations of 2-qubit gates. And there's no reason to suspect that they would all operate with the same fidelity. So I can give you an example of this. Here you can see here's an experiment from IBM where these kind of wavy lines are used to connect the 2 qubits together, much like in Nodar's talk, and there's a kind of low fidelity. Whereas here there's a direct capacitance between qubits that neighbor each other, and you end up with a high fidelity. No one's saying that it's always going to be that way, that direct coupling is always better than bus coupling. But it would be interesting to see if you can use short and long-range gates as part of the same layout. Now, this might also be useful if you're really good at building 1D rows of tightly coupled qubits that you then connect out the endpoints to some other system. But this is maybe in the future works. All right, so let's make a code that has multiple length scales in it. That we can have a short-range set of operations that we do, and then some other operations that are long range. Right, so here's what we're going to do at short range. We're going to implement the 422 code, which has 4 qubits, protects 2 logical qubits, and has a distance of 2. And the distance of 2 means that the weight of the smallest logical operator is 2. So here are the stabilizers, x, 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 and z, 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 z on a square, kind of like in the color code hint. And then here are the logicals, just any side of the square, or any weight to x or z or y on the square will produce a logical operator. And then at long range, we're going to try the Toric code, which is a version of the surface code that's simpler for theorists. Here, qubits are on the edges of the graph, so they're on these little lines. There's a qubit here, for example. And then the weight 4 stabilizers from earlier, this was also rotated 45 degrees, can I keep up? So there's still weight 2 overlap between the stabilizers, just like they were the sides of a square. Only now, X's are on some little stars, and Z's are on these things called plaquettes. We call them plaquettes because square isn't fancy enough. Right, so let's mash these things together. Start off with a square lattice. If we put a Toric code on here, there will be qubits on the edges, but instead we're going to put one of these little 4-qubit units on each edge. And now the qubits are going to be in the corners of the squares. Right, so the n of my code, number of data qubits, has gone up to 4n. Right, so now I encode these in the 422 code. There are now x, 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 and z, 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 z stabilizers on every square. And now I'm going to take the logicals of that code and encode them into surface code stabilizers. Right, so and because my logicals are distance 2, right, here are the logicals sitting around, I'll get a weight 4 product, like 1, 2, 3, 4, of logical operators that are sitting there, right, for a total weight of 8. So right where I had a plaquette stabilizer before, now I have, weight 2, weight 2, weight 2, weight 2. Where I had a star stabilizer before, I have weight 2, 2, 2, 2. So now I have some octagons, but I don't have both kinds of octagons, right? I have Z octagons here, I'll have an X octagon here, but I'll have no Z here and no X here. And that means, let's see, that I have a pair of logical operators that look just like the Toric code operators, except they're twice as long as they used to be, because now there's a chain of square sides instead of a chain just of edges. And there are some leftover logical operators sitting on the squares that commute with everything, but they don't do anything other than that. So, not all of the eyes are fully glazed over. Let's continue. This looks a lot like a color code, and so Barbara got really mad at me because I got distracted looking at color codes for a while. It turns out that if you take the remaining logicals and you encode them into a second Toric code, the result is a color code on a torus that protects 4 logical qubits. Right, so you take these, so this is where an X octagon would be. There are Z gauge operators, and if you encode them into Z, 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 you end up with a Z octagon. Likewise, you can end up with an X octagon here. Now the code is fully self-dual, symmetric between X and Z, so it's a color code. Now, I could do this for any lattice where every qubit is on a square. So I can do this with surface codes. I can get rid of the Toric boundary conditions. The only catch is that I need 2 logical qubits. Here there are X stabilizers. Here's a Z stabilizer. And then if I encode this guy with the squares, I end up with a color code that looks, looks like 2 triangular color codes stitched together, right? Just like you would cut a sandwich. Normally color codes are triangular, right? You diagonally cut the sandwich. But here I got the whole sandwich sitting there together. And we haven't worked out a good way to cut them. Right. Now, caveats. If I tried to do this with a triangle and I put, an X stabilizer here, this weight 1 X operator would commute with everything. I would have a weight 1 logical sitting there. That's not supposed to happen. So let's get rid of that. And then this code doesn't have the same transversal gates as the color code because it has multiple logical qubits. So it does not have all the advantages that a color code that you might expect. But this is the distraction section. Maybe I won't go into too much detail. Yeah, there is also no logical phase gate. These are the best pictures in the talk, but who really cares? You can also do this on a hexagonal lattice. You take a 642 code, which encodes 6 physical qubits into 4. Right? We still have these little edge logicals on the sides. Only here, you get products of the edge logicals, right? Because let's see, Z2 times Z3, that's weight 4, and then times SZ, right? 6 minus 4 gives you 2. You just get the remaining edge there. And if I write out the, let's see, Yeah, if I write out the stabilizers on green and blue plaquettes as products of the logical operators that are on red plaquettes, I get weight 4. Because this guy's Z2, that's Z3, that's Z2, Z3. So this is on a square lattice now, where these are blue squares here, and these are green squares here. They don't look square, but they're square. They have 4 sides and are therefore square. For the purpose of this talk. Now, I didn't invent this. This was already known. This is just a simpler construction of what was already there. And if you don't believe that it's simpler, go read these papers. Or like mop the blood up out of your eyes, you'll believe that this is simple. Right. This likely extends to other stuff, but we didn't have time to really look into it. Yeah, at the conference I was at, somebody gave me an indication that this does extend to 3 dimensions. And maybe you can use this equivalence between color and surface codes to help with decoding, where you could map the decoding problem on a color code down onto 2 kind of decoupled decoding problems in a surface code. Maybe. I don't know how though. But if anybody's interested, yeah.
Why do you use the name gauge operators?
Tradition. Gauge operators, well, okay. It's in the same sense that, choice of gauge doesn't matter. So if you want to choose your code space, you can choose to be in one eigenspace of a gauge operator or the other, and it doesn't affect the performance of the code. So in that sense, they're like gauge operators. That's probably what I just said was a little wrong, but they're operators that you don't care about. I prefer to think of them as just little logicals in which I'm not going to encode any information. Yeah.
Are you saying if I take one of these two-fold codes where I haven't actually got a gauge operator foundation, that I can just take this code and perform logical operations on it, and regardless of which code space I'm sitting in, everything will work perfectly fine, and I won't come in unwanted effects.
If you want to do one of the original gates from the color code, you might have to fix the gauge. Right? So to measure the gauge operators and make sure you're in a certain eigenspace. There are logical gates, though, that are straight up transversal. So if you do a transversal Hadamard on the physical qubits, the data qubits, you end up with something like HH swap on the logicals. So that gate you could do transversally, but if you didn't want to do the swap, you might have to do some gauge fixing. Right, but then decoding is the key word here. So let's get back to work and decode the code that we just invented instead of looking at some other codes all day. The first scenario that we're going to decode against is what happens if somebody just drops a bunch of X and Z errors, uncorrelated all over the lattice. Again, this is due to tradition, not because of any physical model. But you can get down to a condensed matter model simply this way. And you'll notice that if you have a weight 1 error, it results in 2 syndromes, right? So this X is commuting with this square, and this Z octagon here, indicating the presence of this error. This weight 2 chain indicates, that a Z error has occurred. This weight 2 chain indicates nothing because it's a gauge operator. And then long chains, right, also work. You can get an X syndrome here, and if you have some giant string of X errors, you can get an X syndrome up at the top. So this is miraculous, right? This means that by removing some of the stabilizers of the color code, we've got 2 syndromes at the endpoints. We don't have to worry about these Y-shaped objects anymore. We can just take the regular surface code decoder and implement it. So yeah, this thing's CSS. So X and Z decoding can be separated, and you can still get good performance. Right, we got this Toric Code stuff. Blah blah. Okay, this is some details about how to implement the decoder. But let's just cut to the cute graphs. So, on the left we have what happens with the Toric Code. If you have the independent X and Z error model, you get a threshold at around 10%. If you do it with the code that we just came up with, you also get 10%. So, at least for data-only errors, there's practically no difference in performance. If you add syndrome errors, so with some probability the syndrome you get out is just wrong, you can still get a threshold by repeating measurements over and over again and adding a vertical distance onto the way you measure an error chain, right? Because errors can also happen in this time dimension as well as just in space, right? At a horizontal level of the lattice. And there you get 2 thresholds, each of which are around 2.9%. Maybe this one is actually higher. Maybe that's an artifact of the way the X is spaced. the difference isn't really big enough that I would want to get in there and prove that it was higher. Right, but the thing we really care about is circuit-based errors. So we have to mess with the circuits a little bit. Right, and if I have an X error, it starts at here. Right, when I run this CNOT gate, it becomes 2 X errors. This means I can reorder the CNOTs so that errors that propagate will become gauge operators instead of some string perpendicular to a gauge operator, which would be a high weight error. Right, so I can make sure that if a random event occurs, that random event is like a little gauge operator, and it won't matter. Can't do that with the octagons, but whatever. So if you use this circuit to decode, you're not supposed to understand this, just that it takes 8 steps is the point. You end up with a Toric Code threshold, right? So this is a 4-step circuit of around 0.6%. But here you get around 0.27 or somewhere in there. And this is important, that's why it has error bars. If you double up the ancillas per octagon, then you can do a faster circuit that only takes 5 steps, where the first step is to do a CNOT between the 2 ancillas in order to get these into a bell state. Right? If you squash the circuit down in depth, you can end up with a much better threshold of around 0.41, 0.4%. Almost the same as the Toric Code in this scenario. Now, the last graph, which nobody ever understands, if I triple the octagon error rate, I can end up with a threshold that's above 0.2% for the square error rate. This means that if you have short-range gates that are 3 times as good as your long-range gates, then effectively you're at the same threshold as the Toric Code would give you. And so that's a bit of standoff between the error rates for the long gate and the error rate for the short gate. But it matches with this 99 versus 94% fidelity picture that we saw earlier. So maybe something like this would actually be useful and not just be cool for theorists. Right. Well, to conclude, most of these are for theorists anyway. Yeah, you can concatenate codes and understand them better. There are in-between thresholds, between this kind of 0.1% and 1%. That's a cool thing to look at. So now what else should we do? Adapt a bunch of adapt a bunch of advanced decoding techniques that have been used for surface codes onto this code, onto color codes, onto everything. Decode all the things. All right, and with that, see ya. I'm actually done. Okay, there we are. Are we still on time, actually?
Yeah, it's time.
Okay, questions?
10 minutes per question.
You introduced, say, well, let's just use the extra ancilla, because then everything will be better. But I would always say, well, if you're introducing extra qubits, why don't I just go do my same old, very compact, nice surface code, just do it larger distance to perform better?
Yes.
What's the trade-off? Why would you do that?
Observe. This was a comment I got from a referee. This uses the same number of ancilla qubits as a surface code of the equivalent distance. So, like, for the same distance d, you can do it with these, squares, which multiply the distance by 2 and multiply the number of qubits by 4. Or you could use a surface code that's twice as large, which would multiply the distance by 2 and multiply the number of qubits by 4, because n equals d squared for the surface code. And it turns out if you count these ancillas, it's the exact same. So actually you're using fewer if you use the 8-step circuit. But then you're restricted to a higher minimum distance. So it doesn't, surface 17 would still be your smallest experiment.
So if I understand your answer correctly, it means as soon as you go to higher distances, you're better off using this than to use surface code. Is that your plan?
As long as you have sufficiently bad long gates and sufficiently good short gates, then you're better off using something like this. Or if for some reason you have really wide classical control hardware that has to take up a lot of area on the chip, so you stretch out and use a long bus, something like that. I don't think you have this problem in transmons, but maybe the quantum dots do. And there was a second question.
Yeah, I was just wondering, so if you just take the color code and you take off and you just split up your X and Z errors into, those so you split them up in half, do you get something that looks like blossom decoding, and then you can run like blossom QuTech and
Well, there's an idea related to this that does work. which came from Nicolas Alphonse, who's someone you should read his papers, sharp guy. But what did he do? So he worked on the shrunk lattice, which is where you take one of the colored tiles and ignore it. And there you can get, right, if you cut out one of the 3 colored tiles, you can get syndromes that appear in pairs. But you have 3 possible colors of tiles that you could shrink, so he'd solve the 3 actual matching problems that result and take whichever one gave the lowest weight error. That turned out to be an approximate decoder that doesn't get the highest possible threshold you can derive from. Yeah. Now, if you do like, what's that thing called? Parallel tempering, right? Some advanced Monte Carlo. You can derive the optimal threshold for independent data and syndrome errors. For the Toric code, it's around 3%. For the hexagonal color code, it goes up to 4.5%. So there is a big gap that we're not hitting with efficient decoders, and it will be interesting to.
For surface, it's like 10.
Sorry?
So what is the equivalent for surface?
3%.
Oh, okay, sorry, you said surface.
Yeah.
So you're showing thresholds from something like 0.2, 0.4%. In the beginning you also mentioned this 1% for the Toric code.
Yeah. No.
Why does there always seem to be missing a factor 2 or 3 when people actually make these graphs compared to that 1%?
So the 1% threshold uses a really advanced decoding technique. Well, okay, so I gibberished a little bit about the likelihood of an error being length-like, but that's a pretty advanced calculation. What you have to do is take the probability of an error, which is the product of the probabilities of errors happening on individual qubits, take the log. Now it looks like the sum of a number, right? So some number p, or p tilde, right? P tilde here plus p tilde there, blah, 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 which is just length times a constant. If you have actual gate errors, then the events that happen with probability p are no longer weight 1 errors on data qubits. They're gate errors that now propagate through the rest of the circuit, and you end up with syndromes that might be separated a little bit at first order. If you take that information into account in your decoder and you construct, they call it a metric or a nest, which you can use for more accurate distance finding, right? Length finding between 2 syndromes. Then you can get from 0.6 to 1%. So that's where that.
Why don't you do that?
It's hard, Tim.
Okay. It's already known how to do it, right?
Yeah, sure. Why don't you dynamically decouple your gates? It's just tough.
Okay.
It takes time, and we had papers to write. The thing's already 20 pages. It's crazy.
All right, that was for this.
Yeah.
This question is maybe a bit difficult to interpret, but because I don't really understand this and I don't understand the other result, I will ask you about it. So there's this result from Simon Benjamin we'd like to quote for our group because we like this network model where we have some small qubits that we control well and then very long distant links that are very bad. But I guess that result is not necessarily a surface code because it allows arbitrary network models.
Well, so if we're thinking of
do you know about this result?
I think okay. We might be on the same paper. They had like a kind of big cluster of qubits that you could control really well, but then you would have to separate it along like some 1D cuts and distribute entanglement across the cuts. This is what they were saying, right? Okay, yeah. So they had big clusters of high fidelity qubits, and we have really tiny clusters of high fidelity qubits.
Okay, that must be a different paper. I guess my question is maybe more general. What happens if you go away from the surface requirement? Just go to network arbitrary.
An arbitrary network, non-planar?
Yeah.
Then I would urge you to read the CNIL paper where you can get a 3% threshold versus gate errors using a concatenated code, which is really a no position, like completely unaware of where the qubits are model of fault-tolerant computing.
Do you get transistor gates?
I don't think we do, no. Although I'm not so confident. The decoding is also crazy because you use concatenated error detecting codes, and like once you've detected the error at enough levels, you can correct it. But yeah, you're not correcting errors at any one level. All right. Are there any more questions? All right. If there are.